Hello. Today we are going to round out the assessment module with just talk about a couple things, evaluation and ethics. Hi, Toots. Sorry, we have a special guest today. Oh no. Okay, sorry. Hi. Thank you. I appreciate that you love me, but now is not the time. Okay, sorry, I guess this is just life. So I'm gonna just keep going or start. So yeah, this shockingly is gonna be about 2 chunks evaluation. How do we assess our claims? And some basic ethics. So 2 objectives. We'll discuss evaluation using significance testing and effect sizes. And then we'll talk about some of the ethical issues related to assessment. And I swear this is the last kind of chunk on statistics. I know that this is not what you signed up for. Well, you didn't know you were signing up for it. Let's talk about what significance testing is, because it's going to come up. You've likely heard it in really any science class, or, well, any social science class, that something was statistically significant. What does that mean? So in it, guess who's sitting on the keyboard? Tukes. Excuse me. Hi. Well, let's get back to... Nope, that's not what I want. Okay. Yeah, I'm gonna keep this in, because I don't feel like resyncing. Alright, so here's where we were. Statistical significance. Oh, we've moved on. Okay, so he'll probably be back. But yeah, that's Tukey for you. So statistical significance is this idea that a result is real, that it's meaningful. But from a more technical standpoint, what it is a probability. It's this idea that a result would only occur by chance 5% of the time. That's the basic idea. You want your result to be meaningful and not just random chance, but things happen. Unusual things happen. So as a field, personality psychology and most of psychology has decided that 5% is the number we're comfortable with. So we're okay with 5% of all the things we say are statistically significant, that 5% of the time we expect the result to be because of chance. So if you do 100 studies, 5 of them probably false positives. Now we do all of this within a null hypothesis statistical testing framework. Now, for the Bayesians in the room, I'm sorry, we're covering a frequentist approach. I'm happy to talk to you about what the difference between Bayes and frequentist is. I'm agnostic. I tend to publish with frequentist approaches because that's what psychology does. But I really like the Bayes stuff. So null hypothesis significance testing, NHST, is the traditional method of statistical data analysis. It's got that whole, how unusual is this statistical result that we got? Other areas have a little different phrasing. And the biggest challenge here is how backwards it feels instinctively. So what null hypothesis statistical testing does is determine the chance of getting the result that you want. You pose a null, which is nothing happens. So compared to a baseline of nothing was actually happening, there was no real effect for your study, the chance of getting a result that looks like something's happening, we use the rule of 5%. Other fields like neuroscience tend to raise the bar by making their false positive rate 1 in 1,000, 1 in 100, 1 in 20 is the lowest that you can really go and get away with it. And like be able to justify like your p-value, which is what it's called. So there are a lot of criticisms of this method. I think it's more of a problem with research process than the method itself. I think if people really understood that it's 5%, so you should replicate everything, we would be okay. But there's a lot of criticism because people don't do the stuff you're supposed to like replicate your findings to make sure that it's not that 5%. So p-value, or as the book calls it, a p-level, is the probability of obtaining a result from a statistical test if there really is no difference between the groups or no relationship between the variables. There's some nuances here, but this definition is not incorrect. And it gives you the basic idea. There's way highly super technical definitions that I'm happy to talk to you about, but you're probably not happy to hear about them. So essentially what significance testing is telling you how unusual your data would have to be, or how unusual your data are, if there's actually nothing to see here. That's why people are more impressed by p-values that are really tiny, so like p less than 0.001 suggests that the data are really, really unusual. The more unusual it would be, the more likely it is not to have that been the case. That's the idea. So there are problems with this. Big problems. And the field is kind of reacting at this point, so it's probably a healthy medium. But right now we're in a sizable chunk of people really want to do away with this technique because of these limitations that people don't tend to remember. So significant doesn't mean strong. It doesn't mean important. It means how unusual it is. That's it. And there's no such thing as very significant or like kind of significant. It's a decision rule. Either it's past your 1 in 20, it's cut points. It's a decision rule. There's no like wiggle room. Either it passes the bar and it's less than that 5%. So it's below our rule. So it's more unusual than it's an acceptable level of false positive. If it passes that, it would have to be like even more unusual. So say it's p equals 0.03 under a decision rule of 5%. So we would reject the null. And the null is that there's nothing happening, that there's nilch. There's no meaningful effect of your experiment. So the p-value of 0.03, so 3%, we're willing to risk it. That 3% is low enough that we're okay with it. We're like, okay, it's probably not the case that nothing is happening. That's it. And if you are above that, so if you have a p equals 0.051, your data are not unusual enough. So you can't reject your null. And there's some language that makes this a pain in the tuchus. Can I say tuchus on YouTube? Pain in the tuchus. That, like, right, if you're on that border, 0.051, it is not unusual enough. You can't reject the null, is the language that we typically use. There's other versions of this called, like, failing to reject. I don't like because it has a value judgment. But in psychology, we really want to reject the null. So when we say something is significant, that means we rejected the null and that we are comfortable with that level of chance that it's a false positive. Unfortunately, people don't view a p-value as a yes-no. They interpret the number instead of viewing it as a decision rule. The criterion for 0.05 is pretty arbitrary. Like, that's not even what Fisher used. His ends up being like 0.0625 or something. 5% is arbitrary. What if we put it at 0.06? Then that study, some psychologists will call marginally significant because it's really close and they really, really, really want it to be significant. They really, really want it to because then they can publish their paper. That doesn't cross the threshold, the 0.05, but it crosses a 0.06. So, and it's just 1% difference between those two rules. And it turns out there are things that influence how small your p-value is. It doesn't have anything to do with how big and strong your effect is. I could have a super significant result. Again, this is the social psych language talking. Like a result that has a p of less than 0.0000001. So like super unusual. Sample size has an effect. So if you collect more data, even if you're the teeny tiniest effect ever, like I use the correlation between height and intelligence as an example, because I've seen papers where it's really significant. And it's because their samples are huge. But if you were to look at like what the correlation is, what the association between those is, it's 0.05. If that. It's tiny. It's barely predictive of intelligence. And it's because the genes are next to each other. Well, there's some height genes that sit next to some intelligence genes. We haven't found all the intelligence genes. We haven't even found all the height genes. But that's the idea. So, like, they move together because they're literally next to each other on the chromosome. It's cool, I think. But when you have huge samples, you can get a significance level that's super tiny. Itty bitty. Tinier than the correlation between height and intelligence. So it doesn't tell you anything about how meaningful the effect is, how big it is, or how important it is. Because some metrics, you need a really big effect for it to make a difference. While in other cases, like a tiny little relationship can have huge difference. So let me do a tiny effect example. The relationship between anything in longevity. So if you can improve people's like exercise routines, if you marry an active spouse, the spouse will make you more active. Having an active spouse, even though the effect is small and tiny, like can add even just 6 months to your life on average. 6 months is a small effect in the scheme of like 100 years. 6 months, so half a year, is a tiny effect. But it's pretty meaningful. Even like 1 extra month to live would be awesome. Because most of us like living. So significance conveys how unusual the data is, and that's it. Compared to like business as usual. That's it. If you read into it more deeply, ooh, that one's very significant. Or that one's marginal. It defeats the purpose. That is not what significance testing is for. Sorry. I have strong opinions. So more problems with null hypothesis testing. Non-significant results are often interpreted as no result. The fact that it's non-significant means that there is no relationship. That is not what it means. So, like, if you have a p-value of 0.1, so 1 in 10 times that non-significant correlation is still meaningful. It just provides information about the probability of errors. Now, you'll notice I like to be a little grumpy about it's a purposeful teaching technique to highlight that there are disagreements in the field, that nothing is set in stone. Even something seems so obvious and simple and like procedural as statistics has nuance and debate. So that's why I do it. That and I also disagree so I'm going to tell you. So the preamble for this is I don't like the terminology type 1 and type 2 error because they are unintuitive. Type 1 error is a false positive. What it is deciding that one variable has an effect so that there is a meaningful relationship when there really isn't one. So you say it's true. You say that there's a true relationship between height and intelligence. But in reality, so our p-value maps onto type 1 error, which is a false positive. So you're saying it's real when in fact it's not. Now, type 2 error is deciding that a variable doesn't have an effect on a relationship when it actually does. So, in this case, it's the flip. So you say that it's not true, but it's actually true. So, like, that would be me saying, oh, the correlation between height and intelligence, oh, it's not significant. It's not a thing. But in fact, it is a tiny correlation, but it's still real. So, it's a trade-off. So, a type 2 error is a false negative. Type 1, false positive. Type 2, false negative. Way easier to remember. Unfortunately, many psychologists really love this terminology because that's what they were taught. So they will teach it to you, and they will expect you to learn it and teach it to the future. Even I am teaching it to you because other people use it, and I don't want you to be underprepared. The heart of it is type 1 error, false positive. Type 2 error, false negative. So when you have a non-significant result, it is hard to tell if it's a false negative. Because while our p-value is great at like giving us an actual number of, okay, here's how unusual it would be in a world where there's not actually a relationship, type 2 error isn't built nicely in, and it turns out to be like way higher. The rule right now, and of course I have problems with this because I have problems with everything, is 20%. 20%. So 1 in 5 studies won't find something that's there, which is pretty expensive. Now the flip of type 2 is power. And so that's the ability to detect a meaningful result and actually say it's meaningful. Power. And we have a problem with psychology. So essentially we find the effect 8 out of 10 times, 4 out of 5 times. Which I think is pretty expensive. And that's the ideal. Most studies are very underpowered. It's almost suspicious how we find so many significant results. More so finding significant results than we should from a power standpoint. So it's hard to tell because there's no like magical built-in like number the same way a p-value is if your result is stable or due to chance. And even if it's significant, it could be just not important. Like height and intelligence. Sorry, I read a couple papers on it like really recently, so that's my shtick right now.